For the past 3 months, our team has been tackling the challenge of designing, building, and testing a rocket, the Athena 1. The Athena 1 has been engineered from the ground up to fly smoothly and gracefully by directly controlling its flight path. At the bottom of the rocket is the Thrust Vectoring Control Unit, or TVC. This assembly adjusts the direction of the rocket's thrust. By adjusting the thrust vector, the Athena 1 can return to a vertical flight path in the event of some disturbance.
Hey, I'm Connor Bayless. I was the primary designer of the gimbaling system. It's a 2-axis gimbal using 2 stacked servos, which are controlled by Parker's electronic system. One of the challenges was making it lightweight enough and compact enough to fit in the small frame of the body, but I think we've achieved a good solution with a sort of pin and rail system, which is able to vector the thrust as the PID system deems appropriate.
Hi, I'm Parker Ensing, and I'm the lead designer for the Athena 1 rocket. Because our rocket uses thrust vectoring, we have to have an advanced onboard flight computer that ensures that proper feedback control is being used to steer the rocket. In order to accomplish this, I designed our flight computer that uses an Arduino Nano, as well as 2 sensors, an IMU and an altimeter, to determine where the rocket is above the ground and what orientation it's flying in. All of that data is processed by the Arduino, which then tells the servos how to respond to any kind of disturbances or differences between the desired flight path and the actual flight path. A few key points about our rocket. You can see it standing in the background right here. It's rather large, with the boosters attached and the engines loaded, which they aren't right now. It'll weigh about 4.93 kilograms, so about half a kilogram, which is quite hefty. Also, we have 2 different mass moments of inertia, one about the x-axis and one about the y-axis. So about the x-axis, our moment of inertia is 0.00895 kilogram meters squared. And then about the y-axis, it's 0.0103 kilogram meters squared. So that's the kind of system we're working with, and our thrust vectoring control will help steer it around. While the TVC does most of the mechanical work to actually steer the rocket, a lot of the computations occurring in the background happen here in the ADCS, or Attitude Determination Control System. At the core of the ADCS is an Arduino Nano, which can be seen kind of peeking out of these wires right here. The Arduino is pre-programmed with our flight software that includes the feedback control systems for our X and Y rocket axes. Connected to the Arduino are several subsystems. We have sensors on either end. On this side we have our inertial measurement unit chip with an accelerometer and a gyroscope. And then on this end of the rocket we have our altimeter, which tells the rocket how high off the ground it is. On the PCB itself, there are a couple subsystems. There's a power regulation circuit down here underneath these wires that converts 11.1 volts from our battery to 5 volts that can be used by the Arduino and by the servos. Up here at this screw jack is our pyro ejection charge circuitry. So when the Arduino detects apogee, or the highest point in the flight path, it tells the pyro charge to detonate, which releases the parachute and ensures the rocket returns to the ground safely. Altogether, this package is the control system for our rocket. It makes the thruster point in the right direction at the right time, as dictated by the feedback controller.
Hello, I'm Sean Sullivan. Since our rocket requires a gimbal system and an electronics bay, we were not able to use the ejection charges that are built into most rocket engines. And so we had to design our own ejection charge so that we could have a parachute deployment mechanism. So our charge lies here in a bulkhead. And so when the rocket reaches apogee, we have a transistor built into our electronics bay to send current into an igniter into our pyrotechnic charge, which will then pop off the nose cone of the rocket, allowing the parachute to deploy. And in order for us to achieve that right amount of pressure, we have a piston built into the top part of this rocket, so that when the pyro charge goes off, it pushes compression and air up towards the nose cone to pop off the nose cone, and the parachute will deploy, and hopefully will recover the rocket safely.
Seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
Well, the parachute worked. Oh man, one of the boosters blew off.
Let's take a moment to diagnose the Athena 1's flight failure and what might have occurred. We can see right at launch that the rightmost booster begins thrusting before the left and center core do. This is problematic, and this is what induces the heavy bank to the left as soon as the rocket clears the guide rail. One interesting thing to note here is that if you look at the flame of the center core, it's pointed toward the right to accommodate the heavy embankment. This shows that our thrust vectoring control was attempting to do its job. The sensors in the computer realized that the rocket was offset from vertical, and it has adjusted the engine's thrust to try to compensate. Unfortunately, by this point, the differential thrust between the left and right boosters is too great for our thrust vectoring control to even handle, and the rocket enters several heavy spins. Very soon into the flight, the rocket begins to tear itself apart from the forces of the engines as well as the rotational forces. So we can see two of the booster nose cones just ejected. One of the boosters just snapped off the center core. The nose cone of the center core has ejected. The center core engine is still firing, by the way. And that just gets ejected from the rocket as well. By this point, the parachute is starting to get pulled from the rocket. Hasn't deployed yet, but it will momentarily. And there we go. The rocket enters recovery mode. Although the flight of the Athena 1 was not a success by any margin, there were a lot of really great engineering lessons learned. By the end of this project, we have over 70 pages of documentation for the construction, testing, and development of the rocket. We have tons of footage, we have analysis of the failure, we have a solid flight computer and really good mechanical design. So even though things didn't go as planned, this is the kind of thing you want to experience before you do it for real. This is the reason we're engineers, to work through issues like this, to figure out what's next, what works better, and to implement it. Issues like this aren't really problems, nor are they really failures. They're just good tests. They're good ways to check our problem-solving skills, and good ways to prove that we're engineers.